हाय एवरीवन। आज हम ये डिस्कस करेंगे इंटरनल एनर्जी ऑफ द सिस्टम एंड आफ्टर दैट हम लोग डिस्कस करेंगे द फर्स्ट लॉ ऑफ थर्मोडायनामिक्स। तो विदाउट वेस्टिंग आवर टाइम हम लोग शुरू करते हैं द इंटरनल एनर्जी ऑफ द सिस्टम। व्हाट इज इंटरनल एनर्जी ऑफ द सिस्टम एंड व्हाट इज इट्स सिग्निफिकेंस। So starting with the topic or the heading, that is internal energy. Now this internal energy that we are going to discuss, its symbol is either E or U. Some of the authors prefers E, some of the authors prefers U. In some of the books we'll find the use of E, and in some of the books we'll find the use of U for this internal energy. So both can be used, E or U, as a symbol of internal energy. Now coming to the definition part of this internal energy. First thing that we have to keep in mind is whenever we use the term internal energy, the volume of the system should remain constant. That is, when we use this term internal energy, the internal energy is defined only when the volume remains constant. So that means for this internal energy, defined only when volume remains constant. So whenever we use this term internal energy, volume should remain constant. That means at constant volume we define this term. So first thing that you have to keep in mind is constant volume में जो define करते हैं energy, that is known as internal energy. Now coming to the definition part of this internal energy. Now we have a system. Now system is under constant volume. Okay. Now this system, the total energy content of the system due to its chemical composition at constant volume condition is known as internal energy. So I repeat the definition: total energy content of the system by virtue of chemical composition at constant volume is known as the internal energy of the system. So this is total energy content of the system by virtue of its chemical composition at constant volume. That is known as the internal energy of the system, or the total heat content, total energy or heat content of the system by virtue of its chemical composition at constant volume. We can also use total energy or heat content of the system. So by virtue of chemical composition, so look at this, we have this E or U, that is internal energy. So we also say this is total energy or heat content at constant volume. So we also represent by this term. Q represents heat content, V stands for constant volume condition. So this is the energy content total by virtue of chemical composition. Suppose we have an ideal gas inside this a container. So this ideal gas will have different types of energy. So energy due to translational motion, energy due to vibrational motion, energy due to rotational motion, energy due to electron-electron repulsion, energy due to electron-proton interaction, then energy due to chemical bond, and all such type of energies that we can include. That energy is what we call as the total energy contained at constant volume by virtue of its chemical composition. So we have looked at this. Energy due to rotational motion, energy due to translation motion, energy due to vibrational motion, energy due to nuclear motion, energy due to chemical bond, energy due to electron-electron repulsion, etc. All such energies that we can count. This total energy is what we call as the internal energy. Now, as we told you, the total energy contains, we have to include all possible energies that we can access, we can find inside the system. This internal energy is a state function. That means this internal energy depends only on the initial and the final state, and it is independent of the path taken for the transformation of the system from one state to another state. So this is a state function. This depends only on initial and the final states. Now, this being a state function, for every state function, absolute values cannot be defined. Only the change in the values can be defined. Absolute value cannot be defined, but the change in the value during transformation can be defined. So this is for all state function. All state function, the absolute value cannot be defined, but we can define the change in the value of that state function during any course of transformation. So this internal energy is an extensive quantity, meaning thereby this depends on the quantity of the system. If the quantity of the system is less, the internal energy will be less. If the quantity of the system is more, internal energy of the system will be more. That is mass dependent. Mass or amount dependent. So suppose we can look at this, we have a system, and this system is changing from, this is initial state to the final state. This is initial, this is final state. Now system is moving from initial state to the final state. If the initial value of internal energy, that is Ui, this is the initial value of internal energy, and the final value of internal energy, that is F. Therefore, change in the internal energy, delta U, during the course of transformation, this is equals to UF minus UI. So delta stands for change for a finite or large change. If the change is infinitesimally small or very small, then we use this term du is equals to uf minus ui for a very small change. So we can define this change in the value, but not these absolute values at any given point of time. So this is internal energy for a system changing from initial state to the final state. Now this internal energy for a chemical process means for a chemical reaction, we have this a reactant which is giving into the product. So if the internal energy of the reactant, that is suppose UR, and internal energy of the product is UP, then this delta U is equals to UP minus UR, or for a small change du is equals to UP minus UR. But if we have more than one reactant or more than one product, then okay, suppose we have this balance reaction Ma plus Nb, this gives you Pc plus Qd. Let's assume okay, this is a balance reaction. Ab is a reactant, M and N is the moles of A and B that is undergoing chemical reaction. C and D is the product, P and Q is the stoichiometric coefficients. Then this delta U is equals to the summation of the internal energies of the products minus the summation of the internal energies of the reactant. So if you look at this internal energies of the product, that is P times internal energy of C plus Q times internal energy of D, that is the summation of internal energies of the products minus N times internal energy of A plus N times internal energy of B. This is what we mean by summation of the internal energies of the product minus summation of the internal energies of the reactants. This we can define. What is the difference between the final state and the initial state? This is the change in internal energy for this reaction. That is a general expression for a chemical process in which a chemical reaction is being taking place. So this is how we define the change in internal energy of a given chemical reaction, provided the values are mentioned to you. Now this is difference between the product and the reactant. This difference may be positive, may be negative. If the difference look at this difference, as I told you, this is the difference in the internal energies. If this difference may be negative or may be positive. If the difference is positive, we say this is exergonic reaction. Exergonic, we simply say heat releasing, or this is what we call as exothermic. If the change is positive, we say this is endergonic reaction, or heat absorbing reaction, or we say endothermic. So this is how we define the internal energy, and from the change in internal energy we can classify whether the reaction is a heat absorbing process or whether the reaction is heat releasing process. Heat absorbing process is known as endergonic or endothermic. Heat releasing process is known as exergonic or exothermic process. So this is how we calculate change in internal energy. So the point that we have to keep in mind is this is a state function, additive function, extensive quantity means this amount can be added or subtracted. यहाँ पे दिखाई दे रहा है. This is defined only at constant volume condition, total heat content or energy content of the system at constant volume and due to its chemical composition. So its absolute value cannot be defined. So when we have considered an ideal gas in a container, we can consider infinite numbers of energy terms. In all these energy terms, they collectively we define as internal energy. Now, this internal energy is used to define the first law of thermodynamics. So after this we'll come to the first law of thermodynamics. First law of thermodynamics, or in short form we say this is FLOT, first law of thermodynamics. The mathematical statement of the first law of thermodynamics, which says the change in internal energy of a process, this change in internal energy of a process is equals to the sum of heat involved and the work done. This is the first law of thermodynamics. So the total heat content of the system at constant volume, that is change in internal energy, is the summation of the heat content of the system plus work done. This Q is heat transfer between system and surrounding, and this W is the work done. So summation of heat content and the work done, this represents a physical quantity which is known as the internal energy. And if you look at this heat is a path function. This depends on the path taken for the transformation. Work done is also a path function. So summation of two path function gives you a state function, and this delta U, this is a state function. So this summation of two path function, that is heat and the work done, is equals to a state function which is known as the change in internal energy of the system. This is what we call as the first law of thermodynamics. Now let's see what is the implication of this first law of thermodynamics and what are the inference or the conclusions that we can draw from this first law of thermodynamics. So coming to the conclusions. From this first law of thermodynamics. So firstly, for an isothermal process, isothermal process means temperature remaining constant. Now we have this internal energy this in for ideal gas, because we are going to deal with ideal gas, the system is containing ideal gas. So for ideal gas, this U is a function of temperature only. So that is U is a function of temperature, but if temperature remains constant, then this delta U will be 0 for an isothermal process. So look at it, this isothermal process, temperature remaining constant, but this U depends only on temperature. So if temperature remains constant, then delta U will be 0. If delta U is 0 for an isothermal process involving ideal case, then from this first law of thermodynamics we have this Q is equal to work done, or we can say minus of Q is equal to work done. Now let's see the significance of this term. Look at this, Q is positive, heat is positive, means heat is transferred to the system. System is absorbing heat. If the system is absorbing heat, Q being positive, work done is negative. If the work done is negative, that means it is work done by the system. That means if the system is doing work on the surrounding, then the system has to absorb corresponding amount of heat from the surrounding. Or if the surrounding is transferring heat to the system, then the system has to do corresponding work on the surrounding. I repeat the sentence again. If the system is absorbing heat from the surrounding, then corresponding amount of work should be done by the system on the surrounding. Or look at the second, Q is minus, so heat released by the system. If system is releasing heat to the surrounding, then correspondingly system surrounding has to do work on the system. So system releasing energy to the surrounding, surrounding will do the corresponding amount of work on the system. So look at this. If system absorbs energy or heat, if system absorbs energy or heat, then corresponding amount of work should be done by the system, or vice versa. So this has to be very important, this has to be kept in mind. So under isothermal condition, if system is absorbing energy, Q is positive, system is absorbing energy from the surrounding, then system has to do corresponding amount of work on the surrounding. Work done is minus, that is work done by the system on the surrounding. Or look at this, Q is minus, that means heat is released by the system to the surrounding. अगर सिस्टम सराउंडिंग के ऊपर हीट रिलीज करेंगे, देन सिस्टम के ऊपर सराउंडिंग को वर्क करना पड़ेगा. दैट मींस इफ सिस्टम इज रिलीजिंग हीट to maintain the loss of heat, surrounding has to do corresponding amount of work. So if surrounding is doing work on the system, then system has to release energy. If the system is doing work on the surrounding, work done by the system, then system has to absorb energy from the surrounding. This is the isothermal process. So for an isothermal process, delta U is 0 for an ideal case. The reason being delta U is a function of temperature only. So this is ideal gas under isothermal process. Number 2, cyclic process. Now let's see cyclic process means what is happening in a cyclic process. As we have defined during this different types of process, cyclic process means after a number of operations, system is coming back to the initial state. If the system is coming to the initial state, then U initial will be equals to U final, because after a number of transformation operations, system is coming back to the initial starting point. So Ui will be equals to Uf, therefore that is delta U is always equals to 0. So again look at this from the first law of thermodynamics. We have Q is equals to minus W or minus Q is equals to W, same as that of the isothermal process. Same as that of isothermal. Next, if heat is absorbed by the system, system will do work on the surrounding. If heat is released by the system, surrounding will do work on the system. Number 3, adiabatic process. So look at this definition of adiabatic process: a process in which heat involved is zero. That process is known as adiabatic. So for an adiabatic process, this heat will be zero. So according to look at this, the first law of thermodynamics, for the first law of thermodynamics, that is first law of thermodynamics, this delta U is equals to work done. So Q delta U is equals to work done. So if you look at this, or we can say minus delta U is equals to minus work done. So look at the first, delta U is positive, means there is increase in internal energy. Work done is positive, that means if work is done on the system, then there is corresponding increase in internal energy. If the surrounding is doing work on the system, work done on the system, then there is corresponding increase in internal energy. Or look at the second, minus delta U is equals to minus work done. So look at this, minus delta U, if there is decrease in internal energy. So if there is a decrease in internal energy, that means correspondingly system will do work on the surrounding. So if system is doing work on the surrounding, then there is decrease in internal energy. System के ऊपर अगर work करेंगे surrounding, then there is corresponding increase in internal energy. So increase or decrease in internal energy is corresponding to work done on the system or work done by the system. So again I repeat, work done on the system, internal energy of the system increases. Work done by the system, internal energy of the system decreases. So this is under adiabatic process. Number 4, isobaric process. First letter, isochoric process. Isochoric process. So isochoric process means when the volume remains constant, there is no change in the volume during the process of the transformation. That process is known as isochoric process. Now suppose we have an ideal gas, then this work done is defined as minus P external into change in volume. We'll develop this expression later on. For an ideal case, work done is defined as minus change in external pressure, minus external pressure into change in volume. Now, for an ideal case, in isochoric process, volume being remaining constant, so delta V comes out to be 0. Therefore, work done is equals to 0 because delta V is 0 for this isochoric process. So, if work done is 0, then from this First Law of Thermodynamics, we have delta U is equals to Q, or we can say minus of delta U is equals to minus of Q. So again, look at this statement very carefully. Delta U is positive, Q is positive. So if heat is transferred to the system, then there is corresponding increase in internal energy. If heat is withdrawn from the system or system is transferring corresponding amount of heat to the surrounding, then there is a corresponding decrease in internal energy. So increase or decrease in internal energy is corresponding to the heat transfer or withdrawn from the system. Increase or decrease in internal energy of the system, increase or decrease in the internal energy of the system is corresponds to the heat supplied or heat added or removed from the system. So corresponding to heat added or removed, there must be increase or decrease in internal energy of the system. So under isochoric process, if heat is added, there is corresponding increase in internal energy. If heat is removed, then there is corresponding decrease in internal energy of the system under isochoric process. Now coming to adiabatic process, isobaric process, that is constant pressure condition. Number 5, isobaric process. Isobaric process in which pressure remaining constant. So pressure remaining constant, isobaric process. For this isobaric process, look at this, delta U is equals to Q plus work done, as we have defined, work done is equals to minus of P external into delta V. So this delta U is equals to Q minus P external into change in volume, or for a small change we said du is equals to Q minus P external into dV. So the final change in internal energy depends on two terms, that is the product of external pressure into change in volume and the value of Q. So if we know the values of these two quantities, Q heat contained or heat transfer or removed from the system, and this P external into delta V, we can easily define what is the change in internal energy. This difference may be positive or may be negative. If work done value is more than that of heat supply, then this becomes negative, or if heat supplied is more than that work done, then this difference may be equal. So there is increase in decrease of internal energy corresponding to the values of this two terms, heat and the work done. So this is some of the important conclusions from this first law of thermodynamics. So we have to be very specific whether the process is isothermal, cyclic, isobaric, adiabatic or isochoric process. Correspondingly, we can define what is the corresponding increase or decrease in heat content of the system or the work done of the system. So this is the first law of thermodynamics, which simply says the total energy content of the system is equals to the heat transferred between system and surrounding and the corresponding work done on the system or by the system. That is the mathematical definition of the first law of thermodynamics. So using this first law of thermodynamics, let me give you a simple question here. So question says, if 30 units of heat is supplied to the system, if 30 units of heat is supplied to the system, then there is increase in internal energy by 60 units. So if 30 units of heat is supplied to the system, then there is an increase in internal energy by 160 units. Then what is the work done? What is the work done? So question clearly says heat is supplied to the system. So therefore Q is plus 30 unit. Again question says there is increase in internal energy by 60 units. Therefore delta U is again plus 60. Then question says what is the value of work done? Is it the work done on the system or work done by the system? Then we have this first law. So we have this first law of thermodynamics which says delta U is equals to Q plus work done. So therefore work done is equals to delta U minus Q. Delta U is 60 plus 60. Q is plus 30. So minus 30. So this comes out to be plus 30. So work done is positive. If work done is positive means work done on the system by the system. The surrounding is doing work on the system. So this is work done on the system. So this is how we have to use the sign convention from the given data. Heat supplied 30 unit. So this is positive heat. Increase in internal energy, again delta U is positive. So we have to find the corresponding values of the work done. So this is how we use this internal energy, the concept of internal energy. So look at this. This is internal energy. So unit will always be in terms of joule per mole. So change is we define only for 1 mole of the system per mole of the system. So this is its energy should be joule per mole, or some of the units if larger quantity is used we use is kilojoule per mole. Its unit is joule per mole. So if this is defined in terms of joule per mole, then Q must also be defined in terms of joule. Work done is also defined in terms of joule per mole. So whenever we use these thermodynamic parameters, we always define for per mole of the substance. So this is the concept of first law of thermodynamics. Hopefully you understand this concept.